few minutes before the hour, we are going to let this go, let the system run for a while until we get a bunch of people log on, and then we'll get started. So please be patient, and we'll go from there. I'm Rob Pagorni. I'm going to be the moderator for today's FORGE Modeling and Simulation Forum. Just want to thank everyone for joining us today. We've been very, very busy as part of the FORGE team with all kinds of activity that's going on at the site. So what we're going to do today is, before we get started, I'm going to say a few things. First is, if you have questions, please submit your question in the chat box, and we will actually moderate those and go through those at the end. I'm going to keep everybody in the audience muted, and we'll go for that way so we can keep the interruptions to a minimum. I'm going to provide a little overview of activities that are currently going on at the site, and then I will turn it over to our speaker today, Aleta Finnila with Golder, who's going to talk about the availability of the new DFNs, actually all the DFNs for the FORGE site, and that availability and where you can find it. So with that, I'm going to get started right now, and I'll let people just keep coming in as we go. So my system will work for me. So just by way, just the prep or what everyone's appetite, we've actually gone through and scheduled out a monthly presentation for the forum over the next 6 months. And so here's actually everyone on here is committed. So this is a confirmed schedule. So next month, August 18th, we'll have Ben Dyer talking about microseismic modeling for the site. In September, we will actually have the simulation modeling team give an overview of the modeling for the simulation. Also in September is, I'll give an update of the simulation process itself. So we should actually be starting the simulation. The simulations are nominally scheduled to begin early September. So that'll be a pretty active and pretty interesting month in September. In October, we'll talk about ground acceleration modeling from the potential induced seismicity. November, we'll look at some hybrid fracture matrix modeling for well completion evaluations. December, look at impact of injection rate ramp up on nucleation arrest of dynamic fault slip. And in January, I'll actually do kind of a recap of 2021 of all the modeling that we've done and provide a look ahead for 2022. I would say that as the FORGE team or the FORGE project gets larger and gets more active, we start doing more simulations and flow through experiments. If anyone in the audience has a request for a potential or for a topic for a seminar, or would like to volunteer to give one, reach out to me. I'll type my email address in the chat when I'm done speaking. You can reach out to me. I will say that this isn't a venue for people to highlight their own tools or codes. This is for FORGE. It has to be FORGE related. I will also say that we have a number of FORGE Solicitation 2020-1 awardees that are in final negotiation. I'm hoping that a number of those teams will be doing modeling and simulation activities, and I hope to include them into the rotation for the modeling and simulation forum so we can increase our audience here and get some more feedback and discussion among the team. So lastly, I do want to give a little update from the field. So what you're seeing here on my screen is first and foremost on the upper left here is an air photo looking somewhat to the northwest at the site. What's in white here is something that is complete or was complete when this picture was made. I guess of most import is well 16A 7832. The dashed line there is the trajectory of the well, where you can see where the toe of the well lands, essentially about 4,000 feet offset from the wellhead. Importantly, what's going on right now, so we actually have drilled a number of deep seismic monitoring wells in anticipation and preparation for the simulations that'll happen this year. So in the kind of upper right center, 5632, drilled at nearly 9,200 feet. Well, 6872 or 6832 in the kind of center, 1,000 feet. Importantly, what's going on right now is the well 78B32 bottom right. It's in yellow. Anticipated depth is 9,500 feet, where it will also be instrumented with DAS cables as well as other instruments. That well is proceeding. What you're seeing on the right-hand side here is the actual versus the planned drilling of that 78 well. Had to report that actually I've set new drilling records for drilling geothermal wells for the amount of footage in a day and per shift. I don't know what those exact numbers are, but right now that well has been drilled to 8,500 feet. Number of core runs have been taken. it's been logged. They're actually setting casing on that well right now. So if you see at the very bottom here, we're about on schedule. 2,000 foot per bit. I got the feedback here from the team. So that's one of the records that have been set. As you can see, we have very good rates of penetration with intermittent downtime for tooling, for core collecting, or maybe some rig maintenance. But right now, they're getting ready to set the casing. Essentially, we're right on plan for where we thought we'd be for the well right now at about 24 days of drilling. Once that casing is set, they'll drill another 1,000 feet of open hole at the bottom, and then that will be complete. So we're real happy with the progress there. Other things that have happened at the site is over the last few months or even more recently, we have a number, and particularly important to modeling and simulation team, is we have a number of new pressure temperature logs from some of these deep wells. So we have equilibrated logs from 5632, a new suite of logs from 5832, as well as 7832. So we're actually incorporating those into the native state model. And we'll be actually updating the native state model. We won't be talking about that in the forum just because it won't fit. But we're actually taking those logs so we can recalibrate the native state model. And one thing of dismay is the native state model actually it over predicted the bottom hole temperature of 5632 by about 10 degrees C. When I saw the first data, I thought we were off by 1 degree, and I was very ecstatic. But I think at 10 degrees C, given the potential variability at the site, we're still pretty happy with that. But we'll have all those temperature logs in there and have more data to calibrate to actually this week. We're doing those calibrations right now. And the last thing I wanted to mention here as an introduction is, I said already, the stimulation is planned for early September. So stay tuned. There's lots of exciting things going on. It's a very exciting time to be associated with Forge. So with that, I'm going to stop sharing my screen. I'm going to introduce Aleta Finnila. Actually, I'm still sharing. Sorry about that. I'll keep it sharing until I hand it off to Aleta. I'll introduce Aleta Finnila. She is with Golder in the Seattle area. She is our lead for the FMI interpretation for discrete fracture networks, and for working essentially all things that do with fractures and fracture characterization. Aleta's going to Aleta, can I turn it over here to finish introducing yourself, and then I'll stop sharing my screen and you can take over.
Sounds good.
I'm going to mute my microphone just to keep the background noise at bay. But I'll be here. I'll be monitoring the chat.
Okay, thanks. Let's see. All right. Thank you, everyone, for joining us today. As Rob said, I'm Aleta Finnila, work at Golder Associates out of our Redmond office, although I'm still working from home. I'd put my video on if I can. Let's see. There we go. Working from home still, although our office is open, so we're spending some days in the office now. And let's see if I can advance. There we go. The last time I spoke to this group about the FORGE discrete fracture network model was in May of 2020. So we had a reference DFN model at that point, and I talked a lot about how we built it and what we were doing with it. And I promised at that point that some of the DFN files would be made available on the GDR, the geothermal data repository. So we did upload those files, and since that time, we've got a lot of new data coming in from the 2 new deep wells that were drilled. So we've updated the DFN and added some more files to the GDR with that updated DFN. So today I really wanted to, I'll spend just one slide on, what is a discrete fracture network model for those people who the concept is new for. I won't spend much time with that. Then just focus a little bit, I'll just tell you what the changes are from the 2019 DFN model to the current, what I'm calling the 2021 DFN model. And then the crux of this talk is really just to make sure you know what files are available to you for those DFN models on the GDR now, and then to solicit some feedback from the group as to what files maybe you would like to see moving forward to support your modeling work. So I do hope to have a bit of a discussion think about, while I'm presenting what we have on the GDR, think about if maybe you've tried using those files and you're frustrated for some reason, let me know what format of files would be better, or what types of files would you like to see there. So let me just jump right into my slide on what is a discrete fracture network model, because it might be a little counterintuitive to people that the primary objects in our model are actually void spaces. So we're very much interested in the natural fractures of this granitic system, because the flow of fluid in our geothermal system is going to happen in these natural fractures, either in the pre-existing fractures or in those that we create with hydraulic stimulation. So being able to model those fractures in as much complexity as possible has proven valuable in the past. So when we say it, we talk about a DFN, we're talking about explicitly representing those fractures, and we still have to simplify them. So in the models, you'll see here, individual fractures are represented as hexagonal planar features that can connect with each other, and they have certain properties. We describe them with their shape, different sizes, their orientation in 3D. Then we can assign properties to them, such as mechanical apertures or hydraulic apertures, give them some permeability or compressibility. And then we also have properties of the model as a whole, where I call these the collective fracture properties, where it's the intensity of fracturing and also the connectivity of the individual fracturing. So those sort of more group properties. So you'll see how we store data about the natural fractures we're collecting from the FORGE site, and how we export those to the GDR for your use as we move forward. And here I'm just showing the 3 deep wells that we have at the site. The surface of the ground surface is way up here, and we have sort of the granitoid surface sort of oblique to here. And most of our modeling focuses on the deep rock in the granite, and you will often have just these rectangular modeling regions. Okay, so next I'll talk about some of the new data that we've incorporated into the DFN. And I have the 3 wells listed here. So well 5832 is the original vertical pilot well, and that was the data from that well was what we based the initial 2019 model off of. And we've done some further analysis off that data that has improved the model. So even though the data is not so much new for that well, the analysis of that data has been recently completed and incorporated into our understanding of the natural fracture system. Then wells 16A and 5632 were new in this last year. And so we have a lot of new data coming in. We've got FMI logs that are giving us more information about the fracture's orientation, intensity, and actual locations for those that intersect the well set. So I'm calling that a discrete fracture set, where we actually have a set of fractures where we know their location and orientation. We also have more information coming in from the 3D far-field sonic logs, and certainly refinements onto the geology model with the lithology coming from drill cuttings. And also we can do sort of lithofacies characterization from the other log data that's coming in as well. So the gamma logs, like the mechanical logs, and the temperature logs can also be useful for interpreting where you might have more fractured zones than others. So well 16A and 5632 have provided a lot of new data. So let's just go through some of the highlights on the changes to the model. We'll start off with fracture orientation. In the 2019 model, we had identified 3 different orientation sets from that, the FMI data from 5832. And with the 2 new wells, just looking at all the orientation information we have, we've added 1 more orientation set. So we we now describe 4 natural fracture sets by orientation. So we've added a set and we've adjusted their relative concentrations somewhat. This is the table that's still on the website. So we'll need to update the website information about the DFN model. And then this new information is going to be highlighted in the upcoming Geothermal Rising Conference, which is going to be in October of this year. We'll have a paper out that describes the new model in more detail. So I'm showing here the upper hemisphere stereo nets showing the orientations that we're collecting from the deep part of the reservoir from the 3 deep wells we have. So the stereo net here on the left is showing the data we had for 5832. So that hasn't changed, where we have 3 sets. It's a little, doesn't show up so much here. We've got this very strong east-west striking vertical set here, this north-south striking steeply dipping west set here. There's another one, it just doesn't show up here, that's sort of on this side. But the really new data came from the inclined well. So well 16A deviates about 65 degrees from vertical when it's in the deep part of the reservoir. And we're picking up this new set here. It's vertical, it's oriented in such a way that it's picked up very readily, given the orientation of 16A. So we're seeing this vertical set very strongly here, and we're not really picking up the other sets so well, and we're ascribing that to some bias in the FMI data. The FMI resolution wasn't quite as good in 16A as it was in 5832. So we don't think that those other sets aren't there. We think that we're just not picking them up as readily. And then if you go to the new vertical well on the other side of 16A, the pattern there looks very similar to what we were seeing with 5832. So we're getting some reassurance that the rock is the same across our reservoir, and just the different wells are sampling different sets a little bit differently. Looking at the fracture size parameterization, over here in the 2019 model, we were basing our size parameterization solely on the outcrop data that we had from the nearby mineral mountains. So from that outcrop data, at the time we were reporting on this DFN, the trace length data that was measured actually fits a log normal size distribution very well. But if you look at fracture traces in a certain size range, we could fit a power law distribution to that, which we thought was more likely. But we kind of went back and forth on some of our models, whether we wanted to use a log normal size distribution or a power law distribution. We did further analysis of the FMI data in log 5832. And so for our updated DFN model, we've been able to look at the fracture intersections from the FMI log and looking at the statistics of whether fractures fully penetrate the wellbore or partially penetrate the wellbore. We can do some forward modeling to better define what the fracture size population is. And let's see if on this slide here, I'm showing some of that forward modeling work where we have our DFN surrounding a well borehole. So you're seeing a whole bunch of fractures here with a power law size distribution. And then we identify fractures that actually intersect the well bore. And then we can identify which, given those fractures, if we're fully penetrating the well bore or partially penetrating, we can collect statistics in these DFN realizations and compare that to what we actually see in the FMI log. And from that work, it's very clear that the log normal distribution that was fit from the outcrop data does not match the fracture intersection data very well. The power law distribution does, and in fact, it gives us some very good constraints on the minimum fracture size we're probably sampling in the FMI data, which proves to be very important for adjusting the intensity of our DFN as we decide to make certain size minimum cutoffs in our model. So that's, I think this work has been very valuable for refining our size parameterization. And that's reported in a paper that was just presented at the ARMA conference last month. So the reference is there. So the fracture intensity has been adjusted as well, because in the 2019 model, we only had data from one well. And now we have the information from the 3 wells, and our intensity for DFNs of different sizes has been adjusted based on the size parameterization we've done. So if you see the overall intensity in the 2019 model, if we talk about intensity as being a P32 value, where we talk about P32 as an intensity measurement, where we're talking about the total fracture area in a particular volume. We actually get intensity measurements starting from a P10 value, where we're actually counting the number of fractures that we intersect in a wellbore, and we translate that to a P32 value based on the relative orientations of the boreholes and the fracture sets, in order to get an intensity measurement that you can easily compare from well to well. So we like to talk about intensity in this P32, this fracture area per volume, as being independent of the measuring source. So looking at the P32, we had a P32 of 2.5 units of inverse meters on that. The new model actually has a total P32 of about half that original one. So the intensity has gone down by quite a bit. And more information that we can utilize in the DFN. It's not, we haven't used it very much so far, but as far as changing the intensity in different regions of the model, we have a lot more information looking at how the intensity varies in these different wells. So we're getting zones of higher intensity, where you see in these plots where you're looking at the measured depth on the vertical axis and the percent of fractures you're measuring. The slope of these indicates sort of the fracturing intensity. So shallow slopes on these lines are higher fracture intensities, steeper slopes are lower fracture intensities. You can start to correlate zones of higher intensity and lower intensity across the 3 wells to build a more nuanced version of your reservoir. Instead of being one homogeneous mass, we can start putting in zones of higher and lower intensity. I'd say that hasn't been realized yet, but that's probably coming soon in the next few months. So keep your eyes peeled for that. And then lastly, the other sort of update we've done is for assigning fracture apertures. In the 2019 model, we did a simple assignment of apertures just based on the fact that we would like to have a total fracture porosity of about 0.5%. So we just assigned individual fracture apertures such that they would meet that value. We have some new data now. So we actually have some measured mechanical apertures from the FMI in 5832. And we also have some hydraulic aperture information from the well test simulations that have been done. So matching the well test results, doing the pressure matching, using our DFNs, we can calibrate the hydraulic apertures such as to, given our DFN geometries, what apertures would be required to match the pressure signals that we're getting. So we have more information. We're starting to separate these two concepts, separating out this idea of a mechanical aperture, which is more useful for assigning a total fracture porosity, where the hydraulic aperture is, connected fracture apertures allowing the flow of fluid. So those values are quite different, with the mechanical apertures being significantly larger than the hydraulic apertures. And this slide is showing some of that data. So from the interpreted FMI on 5832, we've got some measured apertures. This peak here is sort of in the 0.2 millimeter range, with apertures as large as about 4.5 millimeters. Very few. Most of them are in the range of 0.1 to 0.6. And we can plot those up on a stereo net by their orientations as well, showing that there's sort of larger apertures in preferred orientations, which is also useful for assigning apertures to our fracture model. But what we've seen is these measured ones seem to be 1 to 2 orders of magnitude higher than what we need to use to match the well test pressure matching. Okay, so those are the basic changes to the DFN model that happened from the 2019 model to the 2021 model. Now there's 2 big data sets available on the GDR for these files. And I'm going to spend a fair amount of time talking about what those are to make sure you're aware of what is available currently, and for you to start thinking about maybe what's not there and what you would like to see put on there with this new updated DFN. We'll call this data set number 1. And this was using the previous 2019 DFN data. And this provides all the DFN data that was used to prepare a paper that was presented at the Stanford Geothermal Workshop in 2020. And it was also the work I presented at this forum at the previous time, so May of 2020. And this is just a screenshot of its entry in the GDR. On this slide, I show that here's the reference to the paper. So these files are tied very tightly to the work done in that paper. And along with those files on the GDR, so along with the data files for the DFN, I also provide a PDF with a lot of the words that I'm going to be showing in the next few slides, just to explain how to use those data. But I'm going to kind of walk you through it. So I apologize for the amount of words on these slides, but I think it's important to understand that it's sort of it's a little bit complicated. So it's probably useful to spend just a little time walking you through that process. So I'll read this. The FORGE team is making these fracture models available to researchers wanting a set of natural fractures in the FORGE reservoir for use in their own modeling work. And these particular files have been used to predict stimulation distances during hydraulic stimulation at the open toe section of well 16A 7832. And in this data set, the fracture sets are fully stochastic, and they do not contain the deterministic set that matches the pilot well 5832. At the time this DFN was created, we only had the data from 5832. But since the emphasis of this project was looking at stimulation on 16A, we didn't feel it was necessary to include the actual known fracture locations on 5832 in this particular set. All right. So in this set, we provide files for 30 different DFN realizations. And for each of those realizations, we're providing 3 different subsets of files. So we have 2 different modeling regions. We have a larger modeling region of 1200 meter by 1200 meter by 1200 meters, where we're actually including about 2 million fractures that we're generating in that region. And we only included the format on that in the FracMan file format. So that's a FAB extension. We also provided a smaller set. So if a smaller region, 800 meters by 800 meters by 800 meters, that had about 630,000 fractures in it. And also, again, we only provided that in the FracMan file format. Then in the same smaller region, we filtered by size so that we're only including the largest fractures, which are the most important for hydraulic conductivity. And that those sets have about 5,000 fractures in them. And so we're providing those not only in just the FracMan file format, but also as GoCAD surface files and in a CSV format where it's sort of a point data. And I have an example of this later on, but it's point data where each fracture is represented as a single point and then is assigned a fracture radius to assign the size and orientation information. So I think I mentioned some of this. The FAB and FABGZ file formats are the native file format for the FracMan software. When the GoCAD format only includes the fracture geometry, so there isn't a way to assign the hydraulic properties, such as permeability or aperture along with those surfaces. And I just say subsets 1 and 2 when we have, hundreds of thousands to millions of fractures. Those files are available as individual downloads, whereas once we have the smaller sets of about 5,000 fractures, we've got downloads that include all 30 realizations in one file download. And then this is just information for that subset 3, how we filtered by size. So some details there, and you can look at the PDF that's associated with the files for more details there. And just quickly, so you know what these files were used for, this is just repeating kind of how they were used for the paper that I referenced. So given a particular stress conditions, so we had sort of a most likely stress conditions for the SH max, SH min, in the direction of SH max. We explored a range of potential stress conditions because there's still, even now, there's still some uncertainty into the total, what is the regional stresses in our reservoir. So we looked at, let's see, I think there's like 18 different stress states. And then we looked at the 30, let's see, what did I say here? Say this other one. I think, yeah, there's 30 different realizations. Yeah, there's 30 different realizations. And so for each of those, we looked at the different stress states. So there's a lot of data. There's a lot of data that's been put on the GDR. And the PDF file that describes this data set also has tables like this saying, well, if you just want a single realization, if you just want a DFN that seemed to give you sort of average results when it was stimulated, for average results for the vertical extent of stimulation, this table says you might want to look at realization number 20. So you wouldn't need to look at all 30 different DFN realizations. For your modeling work, you might just say, I want to use DFN realization number 20 and go with that for your work. So these tables sort of show, depending on what you're interested, if you want a DFN that's going to give you sort of maximum vertical extent or minimum vertical extent, you might pick a different DFN realization, because given that the sizes of these fractures conform to a power law distribution, you have some very large fractures appearing in these models, and those very large fractures are going to dominate the behavior in many cases. So it's a stochastic process. We don't know exactly where those large fractures are. We suspect they're there. And looking at a bunch of different realizations show you the variability of results, the sensitivity to your modeling work based on the actual DFN realization. So you might want to select all 30 models to explore that sensitivity, or you might want to just say, I want an average one, give me realization 20. So these tables are there just to look at the extent for hydroshearing. There's a table if you just are interested in inflated fractures, so ones that actually take fluid, you might pick a different realization. And we also just catalog this as far as which realizations, how they performed as far as the stimulation volumes. And there's 2 different ways to calculate the stimulation volume based on the fractures that slipped and inflated. You can look at hull volume for surrounding, doing a polygon surrounding all the stimulated fractures, or you can look at a grid slab volume where you only take a certain thickness away from a stimulated fracture. So all that's available. I think it's a great data set. It does use the previous DFN model though. So it is higher intensity than we think is probably present in the site. So now we've come to our second big data set that we put, and this one does use the updated 2021 DFN. And the models that were saved on the GDR have been used and will be presented for work at the GRC, the Geothermal Rising Conference in October. So my colleagues, Pengtu Singh and Branko Dmanjanik and Zorica, they're taking the DFN, the updated DFN, and they're using that as the starting conditions for more complex stimulation modeling. So these DFNs are just used as the starting case, and then they're going through some stimulation, and you'll see the results of those. But I wanted to make these files available to the greater modeling community because anybody who's interested in doing some modeling of well 16A, this might be useful just to provide some starting fractures for you. So this data set's a little different, but again, it's still pretty complicated. There's 3 different realizations of the DFN provided instead of 30. There's 3 this time. And we've started to introduce this idea of giving you the fractures in both global coordinates and a local coordinate system. So in the global coordinates, that's just the coordinates that are existing in the same coordinates we use for the native state model, how we're describing the system. Once we move to local coordinates, we rotate the model and shift it so that the axes of the modeling region align with the principal stresses, and also move it so that the origin is in one of the corners of the model. So you don't have very huge numbers on your X and Y coordinate systems. So in that set, we provide the well 16A well trajectory in the same coordinate system. So we provided both in the global and the local coordinates and the region box surrounding the model. Then we provide the actual discrete fracture sets in the size of a 10 meter to 150 meter radius. There's about 50,000 of them in those files, and we provide those in 2 formats, the FracMan Fab format and also the CSV file as point datas. And then we also provide upscaled properties. So for smaller fractures, so the fractures that have smaller than a 10 meter radius, we go ahead and just upscale those properties to give fracture porosity, directional permeabilities, and a bulk compressibility. So those could be incorporated in your model, but we don't provide those very small fractures as discrete elements. And then also we provided just the original FMI data. So you would also have information about the actual locations of fractures along 16A. And here's just a few slides sort of showing, this is a top-down view of the region in the global coordinates. So you see, well, 16A, it starts here, goes vertical quite a ways, and then deviates, and you're seeing the lateral here, where the modeling region is close to the toe of 16A. And you can see 5832 and 5632 are also in that modeling region. And then a small change from the 2019 to the 2021 DFN models is that the direction of SHMAX, the most likely direction of SHMAX, has shifted just about 5 degrees. In 2019, we thought it was probably a mean of north 25 east, and in this new one, we think it's north 20 east. So you'll see that our region boxes are rotated to align with that. And I include this PDF with those fracture sets on the GDR. So these slides are also available in a PDF form along with the files, the data files themselves. So it just talks again about the fracture orientation. And a key feature of this data set that's different from the last one. So we're using a simplified fracture orientations for some of our modeling work. It's we're meshing our discrete fractures, and it turns out to be numerically unfortunate to have fractures that are intersected too small of an angle. So instead of including the full range of fracture orientations, we simplify the orientation. So that's why I'm often referring to this data set as the simplified DFN, because instead of a full range of orientations, we only have 4 set constant orientations that match the particular set. So we have 4 different orientations matching the sets, but the intensities do match what we think is the real intensity of those relative contributions of those sets. And there's just details on how the intensity gets modified based on the fracture size cutoffs we're using. So given the new power law fracture size parameterization we have, the Pareto distribution is a type of power law distribution. It's just a truncated power law distribution where we're saying we have a power law exponent of 3.2 and a minimum size cutoff of 0.63. And we got this number, I should say 0.63 meters. We got this size cutoff from the forward modeling work that we did. But knowing the size distribution allows us to change the intensity of our DFN based on what size of fractures we're including. So our background fractures that we're just upscaling, that we're not including explicitly, they have the radius in the range of 0.63 to 10 meter range. And those actually account for 96.5% of the total intensity of the fracturing in the model. Because with the power law size distribution, you have a lot more small fractures than large fractures. So we are removing quite a bit of them by requiring this sort of 10 meter radius cutoff. So the fractures that are left in the very large fractures in the 10 to 150 meter size, that's only about 3.5% of the intensity. So this just shows how the P32 gets adjusted for those different size ranges. And then in these models, we are including the actual discrete fracture sets that we know of from the well 16A FMI data. So what you're seeing in these, there's 3 different realizations along these bottom ones, and you're seeing the fractures that are actually identified that intersect the well bore. So we know their location, we know their orientation. We do not know their size. So we assign sizes stochastically based on the size parameterization we're doing. And then since we're only including at the end of the day, the largest fractures, those greater than 10 meters, we're doing a filtering step. And so the fractures you see at the top here, those are the ones that are actually included in the 3 different realizations. So, so we went from, there's 185 fractures identified in the FMI log in this region. So that number is the same for all of these. And then once we assign sizes stochastically, once we only take those that are greater than 10 meters, we're left with 14 in this one, 11 in this one, 10 in this one. And in order to make this all work, since we want to include this deterministic set where we know we have fractures, we want to include those. By the same token, we don't want to include the stochastic fractures that intersect the well. So part of the step of creating this data set was to take our stochastic fracture sets and find out which of those intersected the well bore and remove them, and before replacing them with the ones we're generating from the deterministic FMI set. And this just shows that in this case, sometimes we're losing a little bit of the fracture area. Sometimes we're taking away some of the larger fractures and replacing them with smaller fractures. So this is just acknowledging that happens. And there's ways of compensating for that in the future if we want, but didn't seem necessary for this particular work. This last slide here just shows how the upscaled properties sort of can be handled when you have looking at just the porosity in the region. What this is showing is just the upscaled properties from the very smallest fractures. So I'm calling those background fractures, they're the smallest ones. Then we can explicitly upscale the discrete fractures, the large ones in the 10 to 150 meter radius range. And it's the combination of that that gets you the total final fracture porosity in your system. All right, so those are the there's two big data sets on the GDR right now. And what I'm hoping to do, we've got this new updated DFN model, and I will be putting more files on there, certainly for data sets that we're using in published papers. So those will go on, but there's a lot of, you can see I have a lot of choices to how much I put on the GDR. And it's not clear to me what's useful to the greater modeling community. Here's sort of some questions I'd like to throw out to the group just to get some feedback. We have the DFN parameterization described in published papers. So are these tons and tons of files of actual DFN realizations? Is this useful to the modeling community? Do you want these? And if you do want them, is it valuable to you as a modeler to provide the data sets in both local coordinates as well as the global coordinates? What fracture file formats are most useful to you? Is there one that I'm missing that might be that you would like to have? Should the fracture orientations be fully 3D like we have in the 2019 data set, or should they be constrained to set mean values like we have in the current 2020-21 data set? What kind of models, region sizes are you interested in? Are people interested in having the upscaled fracture properties, such as fracture porosity and permeability for the continuum kind of modeling? Are there maximum numbers of fractures that you include in your model? Like, do you want DFN sets with 2 million fractures, or are ones that only have 5,000 fractures much more useful to you? And when downloading from the GDR, do you prefer one large download or many separate files? I did that differently in these two data sets. And what other, and then just throw it out there. What am I missing? What would be useful to you? And we can sort of flip through these next slides as people have comments on these different things. For the general DFN description, those are going to be published in papers. So the 2019, I have a reference for that where we describe the DFN there. The 2020-21 DFN is going to be described in this upcoming paper coming out in October. So we have that. Local versus global coordinates. This is just a slide that shows how we translate, from one to the other. Fracture file formats. We've got sort of this, innate fragment format here. We've got sort of CSV files, talk about what those look like. Fracture orientations, I'm showing a screenshot of, the full 3D, letting the orientations vary kind of continuously to just picking 4 constant set mean values. It's kind of a difference there. In the upscaled property file format, I can do that as point data. I could do a grid output, and what kind of resolution is useful, 10 meter, 80 meter, what's needed. And then with the GDR format, one download versus many, I just noticed, so in the 2019 data set, that's the one on the bottom here. I did them as mostly individual files, so there's 65 resources to support that. Whereas I bundled everything all together for the 2021 that's on there right now. So that's one resource. So, I'm not sure which is useful to people. All right, Rob.
So we have a few questions here. And I think instead of me reading them off, since it's a small number of questions, and I think actually the first one came from Mark McClure. And Mark, instead of me reading it, why don't you just come off mute and ask your question so we have more of a dialogue here.
Okay, sounds good. You didn't know your preference. Yeah, thanks for the presentation. It's awesome to see all the calibration you guys have done. I had kind of 2 related questions, so I'll just ask them together. The first is, with the DFN, I think FracMan has an ability to kind of sparsen it out to kind of like the percolating fracture network, because a lot of fractures may be dead ends. or isolated. And I'm curious, with your updated DFN, what does it look like if you sparse it out to that percolating network, and how connected or relatively unconnected is that? So that's question one. Mm-hmm. And then kind of the closely related question is, a lot of fractures aren't going to be conductive at all, right? They're going to be totally cemented shut. So only a subset of the total natural fractures will have any conductivity. So, do we have any way of accounting for that or constraining it? And maybe we don't, but, I'm just trying to understand, mm-hmm. If we had a connection from point A to point B, what does that fracture pathway really look like?
Yeah, those are great questions. The first one, so yeah, Fragment does have the ability to find connected fractures, and I haven't done that with this data set because the people on my team using these fractures were doing the discrete element modeling methods where they were able to create new fracture connections. So I wasn't as concerned about giving them a fully connected network. And in fact, I wanted to give them all the fractures because they had the ability to connect fractures that weren't initially connected in the model. That's providing a subset that's only the connected fractures would certainly be an option. And given that the density, the fracture intensity has gone down in this one, there is less connectivity in this model than before, but it depends on what size of fracture cutoff you're going to use. So if you're going to limit yourself to only the largest fractures, say a radius of 10 meters and above, there are some more, there's less connectivity than if you include smaller fractures as well that are, those smaller fractures can do some extra linking. So yeah, I think it would be valuable to show the connectivity of this updated DFN model, and that's something we can provide. But the current data set does not give you any clues as to I did not filter based on connected fractures or not. So they're all the fractures, and some of them are isolated, definitely. And then as far as clearly we've got a lot of closed fractures. I mean, we're needing to break this rock before we're able to get any permeability changes. That's not something that I've assigned in my model. And I'd say, it might be the sort of thing that a modeler might want to take my fractures and ignore my assigned apertures or permeabilities or whatever, and put their own mask on top of them and do a study on that. So that's not something that I have looked at. There's certainly ways, I can think of ways to approach that, but that's not captured in the current data sets.
Okay, thanks so much. Yeah, I ask because I'm always interested in what's the relative role of pre-existing and newly forming fractures, and obviously that's an open research question. But I hope we get some good data from FORGE in the second well and so on to kind of constrain that, and so it'll be interesting to see how it all fits together in a couple of years.
Yeah.
Thanks, Mark. Aleta and Evan, I see your hand up. I'll get to you in a moment. But we did have another question typed in the chat, Aleta, and this one's a little easier, so I'm just going to read it to you. It had to do with what kind of format are some of the fracture networks, and I did respond to that there's GoCAD, CSV, and the FracMan. But are there other options for exports? Like the question that came to me, like is the DWG or other kind of CAD formats available?
So yeah, there are other formats available, and I'd have to look into the specifics. So like GoCAD, some of them allow you to attach fracture properties to them or not. So some of the CAD ones just give you the geometry. So they don't allow you to keep the properties associated with them. So I'd have to look into some of the specifics, but we do have quite a range of export capability in Fragment. So if there, I'd be interested to know specifically what formats people want, and then I could see if I could get them that.
So we got some clarification, like an STL vector type formats. like STL. And I can answer that myself because yes, I actually get handed STL files because that's what we use imported into our simulator. So we get the geometry from there and we actually build from that. So yeah, STL is an option, other kind of either meshed or noded or some, so that there is that a plethora of file types. Aleta, maybe you can actually, we're going to record this. And so when, as the questions slow down at the end, before we stop recording, I know you sent me a list of potential export types. If I can find it, I'll post it in the chat. If I can't, we'll follow it up and add it to this meeting's notes that people can come back to later.
Yeah, so, but it's not enough for me to, well, what I need is, I don't particularly want to export it out in every possible configuration.
Right.
So,
okay.
So what I'm really looking for from the community is, oh, I actually, if one person wanted STL, that'd be one thing. If 3 people said, oh, we need STL, I'd be much more inclined to make that one of the available models. So this kind of form, I'm hoping for some requests. Like, I really would like this format.
Okay, thanks, Lita. Evan, you lowered your hand, but if you're still here, you can please go ahead and ask your question.
Yeah, I just, thanks. So Aleta, thanks for this overview. It's really useful to see all this. And I was going to make a quick comment that I'm super intrigued by your forward modeling exercise to constrain size distributions. That was very cool. Anyways, so actually, could you go to that slide you were just on with all the potential questions?
Oh, yeah.
So the DFN parameterization, yes, it is useful to have that in published papers. Sometimes I just want to have like a quick screen grab or something of the DFN definition. So something like out of FracMan, the exact definition that was used to generate the stochastic network. So yeah, I kind of take your word for it. If it's going to be published in the paper coming out later this year, then that will be useful. But I wouldn't be surprised if I reached out to you before that, just to make sure I understand all the inputs. And it seems like most of them are even in this presentation here. So,
and this is recorded and available, and we'll make a PDF of this presentation. So you will have this, yes.
Okay, that's perfect. PDF of this would be very helpful on the GDR.
Yep.
And then the file formats, as far as I'm concerned, FAB is perfectly fine. You made a comment about would anybody ever actually need all 2 million fractures? And my response is yes. I think that is something we would be interested in, simply because we often like to do our own studies looking for that cutoff, that size cutoff of what is upscaled and what is retained. So I often do like to work with that full file, even though it can be a little bit cumbersome.
Great, it's good to know.
The rest of these, yeah. The upscaled properties, again, I think that's something that we can do on our own. So when you did the cutoff for the 10-meter cutoff and upscaled those properties, was your intent to share that as well on the GDR, to have like a grid that is on the GDR?
Yeah, so I included it as point data. So, I have a grid, and then I just included the properties from the centers of those grid cells.
Oh, I see. So then we could actually upscale those to another grid that may be a different geometry.
Exactly.
Perfect. Okay.
And what kind of resolutions would you like to see in this? I mean, it's kind of model dependent. It depends on what you're looking for, I realize.
Well, I think at this stage, I would be interested in single well models. So not large enough to cover multiple wells, but I'd be interested in looking at something like injection and stimulation of a single well. So whatever the kind of the well pad size would be is probably sufficient. And then, well, now that I say that, then I'm thinking, if you had multiple wells, if it was large enough to cover multiple wells, and you could check inter-well connectivity.
Yeah, we found, I mean, it's really useful to have different sizes, because for the well scale, often I'll want to include much smaller fractures. because just again, it's sort of size. If it's a big model, I tend to go with the bigger fractures. If it's the smaller my model size, I'm just happier to include smaller and smaller fractures. So it's sort of nice to have sort of some different, a big model if you're looking at inner well action, or if you're just looking at well, matching well test information, and having a smaller model and being able to include some of those smaller fractures, I find helpful. So they're both helpful. And what I'm using as my guide currently is what my modeling team is requesting from me. And in fact, before I forget, before it gets much later, let me show you my modeling team members. They're listed here, where Rob's the leader of our team, but we've got a good crew of people doing modeling work. And of course, all this work is being funded by the DOE.
Yeah, and I think, I mean, I can't speak for anybody else. I can just say that for the purposes that I would want to use this model for, I think it's fair to say I would just download the entire region and then just cut out sectors as I needed. So kind of have the full 2 million fractured, 2 million fractures, and then I would just cut out sectors around the individual wells.
Okay, so as big as possible, really, is kind of what you know.
I'm okay with that.
Yeah.
I'm okay with the cumbersome size. That's fine. So, okay, thank you very much, Lita. I appreciate it.
Yeah.
Thanks, Evan. So we have another question coming. It's kind of a follow on. And Shazrad, I'll let you, why don't you just come off mute and ask your question here. Maybe you could just make it easier instead of being in the middle of interpreting.
Yes, thank you very much, Rob. I was wondering if we can have, and thank you very much for the great presentation, Aleta. I was wondering if we can have a small, high resolution model, and also a large, low resolution model, like 100 by 100 by 100 cubic meter with the smallest possible fractures present, and a large model with large fractures, 1 kilometer by 1 kilometer.
And what specific target are you looking at? Are you looking at stimulation of 16A, or are you looking at well tests on 5832? What small region are you interested in?
That's a good question. I haven't studied those yet, but this 16A is the one that you have the alternative models from 2019 and 2021, right? Or that's the
we have a both. We have them both.
Okay, then let's go with 16A.
And as far as the file formats are you okay with the FAB format on files, or do you need CSV format?
I haven't worked with FAB, but I know the software that I'm working with is okay with any vector type ones. I have worked with DWG. I have created my geometry with DWG, but that's a good point that you added. The properties may not come with it, only the geometry comes, but I need the properties as well. So if you, in that list, include which ones bring the geometry, then I can check with my software which one is best optimum choice.
Okay, great.
Thank you so much. Thank you.
No worries. That's all the questions I have that are in the chat bar, or that people raise their hand. Is there anyone else has a question, or even general about this topic or anything else? Since we have, we have this room for another 25 minutes. If I'm happy to entertain any question that might come along, and a large fraction of our modeling team is still in the room. So if there's any further questions, feel free to raise your hand, and you can take the floor.
I've got a question for the group. Has anyone downloaded any of these files yet?
I have.
All right.
One more question. I found you on LinkedIn, but I couldn't find your email addresses. Could you please provide them here on the chat?
Yeah.
Thank you.
Hey, Rob, can you, I don't know if I can do chat at the same
I'll do it. I'll just copy your email. You just
thank you. Yeah, do my email. Thank you.
getting it right now. One moment. So I guess with barring any further questions, we could close for the day. I thank everyone for their attendance. I thank you, Aleta, for the great presentation, doing some great work. I encourage everyone who's here to join us next month. It's really a fever pitch of activity for Forge right now. It's a very exciting time to be involved. We're looking for further information, integration, and input from the community at large. So please, and once again, there's an email address we put in the chat. If you want to say something, even if there's snide remarks, send them my way, or critical feedback, I'll take that as well. It's all taken as positive input. So I thank everyone, and I wish everyone to have a great rest of your day. And thanks again, Aleta.
Yeah, thank you, everyone.
Bye now. Oh, somebody did raise a hand. If you're still there, I'll stay. Oh, good. Are you done, Shazrat, or did you have something else?
No, just a virtual clap.
Well, thank you.
Thank you.
Thank you.
Bye now. I'll leave it live for a moment, Gosha, until people close off, just to make sure we got everything. But I think we're safe to stop recording now.